Oh, yours? Let's check something. Oh, what? Is it like this? Okay, so good afternoon, everybody. Hopefully everyone's had a good lunch. So my project is called a virtual comfort, and we're going to use a persona in a gaming environment to communicate thermal comfort experience to support urban design decision making. And I would be partnered with Hassel for this research. So before I start everything, imagine yourself to be in an environment where it is like an Australian very hot summer's day, around like 40 degrees outside, and when you're on the street, there is absolutely no shade whatsoever. First of all, you'll start to think, okay, I'm in a very uncomfortable environment, and why hasn't any designers or planners thought about actually implementing or putting any form of shade in the area? So this leads to the question of my project, which is the two aims of the two questions, which is how is thermal comfort calculated and what can be used to calculate it, and how will human thermal comfort be experienced and communicated, and what are the variables? Fundamentally, this project will answer the question of how to get designers to experience thermal comfort virtually. Why so is because often architects and designers would understand graphs and data from thermal analysis, but in more often terms, it doesn't really account for the actual post-construction effects. Like to get an accurate gauge of actual comfort sensations, you have to actually spend resources and effort on actually gathering essays and interviews, on surveys and interviews post-construction to actually understand whether it is a thermally comfortable situation or not. So this aim of this research is to be able to simulate this before they go into the design process. So above on the 5 points, there is the ambient temperature, radiant temperature, relative humidity, wind speed, and interaction. These 5 elements will form the fundamental basis of this research. Why interaction is, and also gamification as a base, is because from the words of Ellis in 2000, the research established that, or argued that the current analysis of our environment lacks a quantitative and qualitative value in forming a uniform framework for weather analysis. So hopefully by implementing all 5 of these elements into a singular gaming platform, we can simulate an environment which is near realistic to what a physical real environment should be like. So for this research, I've used the following tools: so Grasshopper, Rhino, Honeybee, and Ladybug tools, and the Unreal Engine. For the workflow diagram, there are 5 steps. There's the model import using Rhino, analysis of model using environmental data. This is again done in Grasshopper and Ladybug tools. The third one is the output. So this primarily focuses on translating and bridging the data from Grasshopper to the Unreal Engine. Fourth is the visualization with the Unreal Engine. So we're going to input data into the Unreal Engine like from Rhino and play around and configure that stuff. And finally is the 2 results. So we can get both static data, so generic standard weather data from Honeybee, and also an experience form of data. So when the actual user uses the workflow, and on the left is the software tools which are correspondent to the actual workflow stages. For this research, I used the precinct of Blackwater Bay as discussed with Hassel. Due to some resource conditions, they couldn't provide with the actual full model, but we did look at one of the projects which Hassel did work on, which is the Blackwater Bay. So from the Infrastructure New South Wales, the C proposal, one of the master plan proposals is indicated on the top, and to translate this into something which is usable, I made a 1-to-1 near approximate scale of that same plan. So next would be the actual Honeybee workflow. So there are 3 stages. So the first up is actually the area zoning. So for here, we'll start to look at allocating specific zones and allocating materials and solving adjacencies. The second part is actually looking at context and using OpenStudio to define context, such as trees, transmittance, importing the weather files, and also exporting to OpenStudio for calculations. And the third one is actually the microclimate generation. So we're going to define the view factors create the temperature legends, and also output mesh layers of UGCI, radiant temperature, and air temperature. For the first stage of the workflow, we will look at some material. So I've made a mock-up material list using some near realistic data sets. So we'll look at certain types of material, their thickness, conductivity, density, heat capacity, and how they will be color coded in the actual model, so it's easy to see. Below some vegetation data. There are some forms of limitations when it comes to these data because this doesn't really account for evaporation, but it is enough to actually generate some sort of results for the sake of this project. So for this project, I used a kind of an iterative testing format. So for the first one, I did a simple model. So this is like a small scale. We're just looking at trees, looking at buildings, and see the actual fundamental processes of honeybee, whether it works or not. For the second step, I looked at actually more different types of trees and actually inputting material formats. So as in from the before in the materials tables, gray here will be for concrete, and green here, like darker green, will be for grass, and below those two charts is a generation of the thermal claim for UGCI, seeing maybe if there are some temperature differences across them. For this research, finally, there's the mesh results for the Aquaportal Bay format. For this research, I used this example, equinox at 9 a.m. In discussion with Hassel, we looked at 3 different time periods, so equinox, summer solstice, and winter solstice. For this example, we'll look at equinox at 9 a.m. So indicated on the left, there are some colors, and then you can match it to the left, which is given the thermal calculations are done, you can see how they would perform under certain heat conditions. This is a mesh result. So there is about 48 different mesh results. So for the sake of this one, we'll show you this one. So prior to actually going into the Unreal Engine stuff, we'll look at actually understanding the thermal and the scoring system. One aspect of this is actually being able to quantify this thermal analysis, so it can be used as like a uniform system before. So it is actually it's uniform across different platforms, so people don't have to think too far. So on the legend, I've given a rough legend and their rough temperature zones and comfort zones. So and given also a score to them. The cooler zones is decreases a bit less than the hotter zones because in terms of comfort, as discussed with Hassel, it is just easier in cooler places for people to feel more comfortable because you can put more clothing, unlike in hotter areas, which is just more difficult to put more clothing. That's why the scores are a bit more varied. Below is psychrometric chart. For professional purposes, this one is also color coded. So in matching with the legend, you can see your current position within the psychrometric chart and gauge what comfort zone you're currently sitting on the psychrometric chart. Using the psychrometric chart, you have to know 2 more things. You can get temperatures from the legend, but also form of humidity. Humidity can be found using honeybees, so that data is gatherable. So the part of the outputs we look at trying to convert this mesh into something which is more usable. So for the Unreal Engine, so there are like 3 steps for this. So first we'll convert the mesh into a PNG using the Ladybug converter, and then we'll use the PNG as a material, and then we'll rebake that mesh on the model, so it can be later used because FBX files and standard Rhino files, when it processed into the Unreal Engine, it doesn't really recognize mesh colors, so and vectors. So this is why this has to be done. It is quite a manual process, so it took a lot of time. So before we go into this for communication, we'll look at actually the Unreal. So before we go into this, we're looking at some model import settings. So during this research, I used Datasmith, so we can easily select your 3D model and then import the file. It is a plugin, so you have to enable it. The content folder, where you can actually edit your content. So collision status, which for physics, which is important if you want to actually play around in the level. Importing meshes such as Flora for a more realistic look. And I'm creating blueprints, so custom blueprints and widgets later on. So a well liner is just so you can see where the things are. And finally, blueprints, which is actual level programming. So now we'll look at some level programming. So for user interaction, the actual part, so you have some level programming, which is the actual inputs which the user can use to actually access specific types of layers and inputs. So you have, so on the right, there's like the summer, equinox, and winter solstice, and the different key commands you can use to access different layers. So UTCI, radiant, and air temperature. We've given the different layers and formats. Below is the widgets. So this is more user interface stuff. So this one, I've showed the example of summer, but you can slide through different times of the 3 different times and also the different specific times. So 9 so the 3 times we were most interested in were 9 a.m., 12 p.m., and 3 p.m. Next would be the level influence. This is what actually we can use to actually influence the user interface stuff. So and the level, so the persona characteristics. If you're going to define the persona, you have to give them some form of characteristics. So for this one, I've used a 2% damage indication to actually impact the current level and overall level, as in to define whether if this character actually enters a specific area, they will take damage. Below is the zone setup, so the actual place if a character actually walks into that zone, if within the boundaries shown on the right, you can actually see that 2% damage or a certain amount of damage actually be taken. So for the actual final results, so again, we'll look at equinox and 9 a.m. So on the top is like a near realistic visualization of the actual model when inputted into the Unreal Engine. You can roam around this and actually explore the area and see what it could be like, what a pseudo master plan could look like in a realistic sense. Below is like a heat map, which is from the mesh results from Honeybee, and this is like toggleable. You can toggle this up and off and off to see whether you are in a specific zone. So in this case, we're in the green zone, and using the legend up there, we can say that, okay, we're in a comfortable zone, so you'll take no damage, and you can refer that to the psychometric chart below as well. We'll go to areas B or zone 2. So this actually walks in a bit. So if you actually walk into it, you'll see in the top, you say, okay, I've taken some damage. Why have I taken damage? The user can actually then toggle up the layer and say, okay, I've taken damage because I've entered a yellow zone. So this hence why I've actually taken some form of damage, to give like a quantification kind of aspect of this. The whole process of this is more or less to give that humanistic nature feel to that, because it is definitely hard to evaluate comfort in terms of just the data and analysis format. So this is why this is done. Is it? Oh, it's almost done. So some limitations, it's just model is geometry built on approximation, some basic human characteristics, tree transmittance is uniform, and the interpretation of data is quite standard. Like it's my interpretation, so it's not really quite as to what the interpreter wants. And, some problems is Unreal Zone program, so you could change different zones, but the value is still the same. That's the thing which, given the time span of this project, is a bit difficult to fix. So, but it's definitely fixable. Next is just some additional other problems. So calculations times Honeybee, given how complex geometry is, it could take more time. There's some accuracies in thermal properties which are more difficult to evaluate since there's evaporation and other status problems, and it's very manual intensive, especially when the manual outputs and the stuff. And some future endeavors, so agent simulation. This one with Hassel, you can actually gauge where pedestrians usually cluster and actually form a more accurate form analysis in there. Some wind simulation to see, because in Honeybee you can gather wind data, but you can't actually see where wind is. So that's viable as well. And some automation when it comes to actually streamlining this whole process. And that's it.
Not a question, just like a comment. I feel like it'd be cool if you could, based on the data, the APW file, you can stream that into the rendering. Say like the APW says it's cloudy, like render the sky.
That's something which I do want to do, but it's pretty hard.
Right now, I'm sure like.
Yeah, it's feasible, but it's just that there's a lot of manipulation when it comes to that data set. So, like, because you have to have a specific time, and the specific time it is being calculated for, because APW files, it's like calculated every hour, so you have to know every hour's thing. Yeah. That's why data gathering is very heavy in this project. And yeah.
Well done. Good presentation. Well done for speaking in within your time frame.
I tried my best.
So Tim, I remember you from first year, and one of the very first presentations you did was, I think, the Smart Cities course, and you just talked. I know you wrote really long essays.
Yes.
And you've got a lot to say, so I think it really refined your what do we call it? Being able to synthesize that information. Yeah, and I think again in Admiral's project, a real challenge as well to communicate thermal output data in a
because for some research from the literature reviews, it's like they're saying that it's hard to actually do it because there's a lack of quantitative values, so you can't really actually know what's comfortable, what's not comfortable prior to actually building it, because like we can see here it's pretty sunny, but we actually have to go there to actually have a sensation to actually know whether it is. But what happens before the design process? Like no one knows. So this project, so what I was interested in this project was to actually see whether I could address this before we actually build the master, because master plans are really big and they spend a lot of money on this. So if this can be rectified before we go into the design process, then I think it potentially could save money before, doing it, and people feel happier.
Yeah, it's super important for designers, clients, stakeholders to really have that kind of knowledge.
Yeah, because with Hassel, they also said, like, if they hand the project to the government, should I keep talking?
Yeah, we should wrap it up.
Shouldn't I?
We can talk in the pub.
Yes, I should edit you. Yeah.
Slightly more flattering. Just get that like.
All right.
Yeah, perfect.
Cool. So I'm Jamie, and I'm doing my project in partnership with How2, which is an e-learning software company. And my thesis is called The Spatiality of Caring, Connecting Disability Services Personnel to Care Environments Through Augmented Reality. So traditional e-learning modules are typically content heavy with low engagement and retention rates. This is because the learning content is disconnected from the physical environment. Augmented reality, or AR, is a technology that can enhance learning experiences by overlaying the learning content onto the physical environment. It has been proven that AR provides a richer learning experience because it makes learning more fun. It enables the user to interact with the learning environment, which develops their knowledge of the content. It also caters to a wide range of learning styles because the learner can see and listen to content rather than just reading it. AR also provides a space for learners to collaborate and experiment, allowing users to play a more active role in their learning. However, AR is still far from being widely used in learning contexts. One of the main drawbacks is the difficulty of developing AR tools as it requires some knowledge of programming. There is also a lack of tools for developing AR modules specifically for education. Disability Services Australia is a company that needs a way to quickly and easily create learning modules which are engaging and can be used in a variety of learning environments. Specifically, they need to create training for the safe disposal of syringes. Therefore, my project aims to explore how AR can be used to enhance learning processes within the care environment of a disability services worker. I will also need to create a proof of concept AR module to train disability services personnel on how to safely dispose of syringes in their work environment. The aim is to create a framework which can be further developed by my industry partner How2 as a template within their software. For this, I will be using Figma to design the prototype and AR.js to develop a proof of concept. So how does augmented reality influence disability service personnel's sense of connectedness and awareness of safety procedures in a care environment? That is the question that I'm going to be answering. So this is my workflow. So yes. So first I'm going to create a custom marker So that is done through uploading like the how-to logo to a AR.js marker training website. So that is the generic marker at the top, the hiro marker, and this is the custom marker I made at the bottom. However, I did have a lot of issues trying to actually use the custom marker. I'm not sure why, but so I just continued the project with the generic hiro marker. So next is the script development. So first, I imported the AR.js and A-frame libraries. Then using AR.js, I created an augmented reality scene where you can define the webcam input and the displayed content. And then with A-frame, we create a video handler and script it so that it is compatible with iOS operating systems. And then finally, you add the custom marker that we created. But in my case, I was just using the hiro marker. Then for when the user actually uses the module, you can see the workflow down there. So to use the prototype, the user navigates to the web page and allows the device to access the camera. Through the live camera footage, location markers are displayed where yellow sharps containers are kept. Then the user moves closer to the container. They can scan the marker. Learning content and videos are then displayed over the live camera view. You can see some mock-ups that I made with Photoshop up above. Yes. All right, so for developing the prototype, one of the main challenges I faced was the lack of resources and tutorials, especially in regards to displaying content other than just 3D models. It's also very difficult to add any graphical user interface elements like back buttons, crosses, necks, and also because the documentation is focused on just displaying 3D models, it's quite difficult. Also, since I have a fairly basic knowledge of JavaScript, I found it difficult to analyze the script and recognize what was not working within the script. So you can see here, these first two videos are my initial progress with the tool. So first I was able to display a 3D box onto the hiro marker, and then I was able to add a more complex model with an interaction button. Then from here, I was able to display an image on top of the marker, but this was very buggy and it would just constantly like turn off and on. And it was also quite difficult to find resources for troubleshooting on this, as most people are trying to just display 3D models on the markers. And then to the right of that, you can see I'm displaying a video on top, which was my end goal for the proof of concept. So this was also, yet again, more difficult for the same reasons as lack of resources. And also I had an issue where it wouldn't be compatible on iOS operating systems due to the security settings for displaying videos. So for the next steps, if I had more time on this project, I would further develop the user interface to be more usable in a real-world context and kind of integrate all the different AR interactions into one learning module to create more of an actual flow, a learning journey. And then but then this can actually be used as a base for how to create an AR template within their existing software, as you can see there, as a block that they can insert, so that any company can easily integrate AR into any learning module for any context. And yes, thank you.
I guess my question would be after all of that, what do you think you've learned?
I think I've learned, well, because I did focus a lot on the actual learning journey. I did learn a lot about like how, like the neuroscience behind learning and the effects that AR have on learning. like how it can really help it. And I think like in like a lot of different contexts, it's really relevant.
Yeah, and I think understanding how to design the content, or how to, what content you need to
Yeah.
communicate the learning. We understand this problem. We deal with it all the time. Is actually the hard part, and stuff like the technical stuff. You know, can get multiple people contributing to help you resolve the technical issue, but actually the complexity of your project is really is the effectiveness of the tool itself.
Yeah.
And which is difficult to test because you can't, use the test it. So you
Yeah.
can evaluate the tool from the perspective of efficiency, quantity of information, like from your own perspective, did you achieve uploading this content to the
Yeah.
So, yeah, it is definitely a project which, to answer the question that you asked, necessitate user testing
Yeah.
at some point. And again, it's really like all of the projects that we've listened and seen today. It's a really important project because it's addressing a really significant issue. Well, it's a really interesting one from my perspective in the context of code because you're taking the skills you've learned here and you're actually applying them in a completely different environment. So we're outside of the AEC industry in this project, but you're applying skills that you've learned in the code. So it really speaks to the possibilities that you guys have in where you go and take your skill set to a number of contexts.
Yeah, I think that's a really good point because this project in itself is really a little bit ahead of its time in terms of AR. Because I don't think it's too mainstream, like accessible for the end users in this case.
Yeah.
Whereas, like VR goggles or AR goggles that come out, or glasses that come out, can make this kind of software or this process a lot more accessible for people to use, especially in that kind of environment. Whereas right now you're kind of like building the stepping stones to that process. Which is really cool because if you take this research and you develop it more, you could be the first person to do something like that for the industry, which is really cool.
Thanks.
Yeah, it should be on. Where's the camera, by the way? Okay. Cool. Thanks. I'm good? All right. Hey, my name is Nelson, and I'm partnered with Bates Smart, and the title of my research project is Improving Material Performance through Topological Optimization in High-Rise Construction. And so why am I doing this for my research project? With the population of cities slowly increasing, more buildings are required to be built or to be built taller to keep up with the need for either housing, office spaces, or even commercial marketplaces. And so as more buildings are being built, more materials are being used or consumed, and the natural resources that are mined and used to make up these materials are slowly being depleted. And so there's a need to design more sustainably, but sustainable design is not a new thing. There has been research done previously on reducing material usage in buildings, either through researching new and stronger materials, or such as higher grade steel or COT. And other researchers such as Fry Otto have researched complex structures such as tree-like structures, which essentially strengthen our buildings
structural integrity while reducing the material used. And so in my research project, I employ the method of topological optimization. And topological optimization is the process in which material is removed where it is not required, given a set of constraints such as the boundaries, supports, and loads. And so as you can see in this example, the beginning geometry or boundary of the chair is set, and it has material iteratively removed from it until we reach that final result, which is essentially a chair we can buy at a local IKEA or a furniture store. And so why is this important? By removing material that is not needed, we are essentially saving material to be used for other uses. And in this case, we can see that the chair is essentially reduced by roughly maybe 90% of the material, which can be used to make multiple other chairs. And so my research question is, how can topological optimization be applied in the architectural design process to reduce material waste while maintaining structural integrity in high-rise buildings? And to answer this, I have set out two objectives, which is to reduce material usage in high-rise buildings without compromising their structural performance, and to create lightweight building structures. And so I have this workflow set out, which essentially is just 5 steps. And step 1 is to generate the geometry. And so the geometries I'll be setting out are the columns, beams, and floor plates. And these geometries will essentially be the components that I will be optimizing through Amoeba. And so here we can see that I've made the columns in Grasshopper with a variable height and width, just to be able to conform to any design work or process. And same with the beam and the floor plate. They have variables which allow it to which allow them to be molded to fit any other project. And so with step 2, I generate the building structure. The building structure is set to have a variable length, width, and height, and variable grid size. In this case, I set out to have a 9 by 9 meter structure. So every 9 meters, there would be a column set in place, and the floor plate would essentially be 9 by 9 as well. And so the next step, I will be optimizing the geometry using Amoeba. And so what is Amoeba? Amoeba is a topological optimization plugin for Grasshopper. It lets us specify the loads, supports, and the percentage of material removed from either mesh, BREP, or surface, as well as some other variables which I didn't get into for this project. And so the first thing I ran through Amoeba was the column. And so I just set up the column to be a 1 meter by 1 meter prism with a 3 meter height. And because of the nature of columns and how they are stacked on top of each other while constructing, the supports on top of on the bottom of the column and the loads on the top of the column were positioned in the same place as the loads applied from the columns stacked on top of each other would be the load applied for the optimization. And so this is essentially what we have here. We have 4 load points on the 4 corners of the top of the column and 4 load points on the bottom of the 4 support points on the bottom of the column with 50% removed, which essentially we get this result as seen in the GIFs. Next, same with the beam. The measurements can be seen on the screen, and the load and in the model, I modeled it so that the beam would be supporting the load of the floor plate, so that the beam would be positioned under the floor plate connected to the 2 columns on either side. So this meant that the load on top of the beam would be the entire surface of the top surface, and while the supports would be located on the 4 corners on either side of the beam. And once again, 50% of the material is removed. And again, with the floor plate, we have the measurements there. As I mentioned before, it's a 9 by 9 meter grid, and the floor height is 0.3 meters. And the cutter on each corners are based on the columns specified before. And so because the floor plate is where there are live and dead loads, it's kind of difficult for me to specify those different live loads as designers, we don't really know where all those loads are going to be. So I just set out to have a uniform load on the entire top surface of the floor plate, and the core, the supports being where the four corners are connected to the column. And so with the optimization done, we have to ensure that these geometries are structurally stable and that they're not being compromised by the reduction in material. And so with topological optimization, material is essentially being removed from where it's not needed. So from this, we can use a stress analysis, which is provided to us from Amoeba, and compare the geometry beforehand and after the optimization to see if there's any shift in the stress values. And so in this column, we can see that the maximum stress value right now is 5.26, and after the optimization, the maximum stress value remains the same. And so from this, we can take it as the geometry is perfectly fine with 50% of the material removed, or we can continue removing more material until there is a shift and we have to stop at that point, so maybe 60%. And so next we have the beam. Same with the beam. We compare the stress levels before and after. So before we have 2.14, after we have 2.22. And so although the stress values increased very slightly, I don't actually know what these what the true measurement of these stress values mean. So it depends on the material used. But from this, we can either take it as too much material has been removed, thus we need to reduce the material removed from 50% to maybe 40 or even 30%. So next we have the floor plate. And so same with the floor plate, we compare before and after. Before was 4.67, after is significantly more at 7.17. And so with this iteration, I had to go back into the design process and reduce the amount of material removed. And so from 50%, as you can see right now, I changed it so that it would only remove 22%, and with 22%, it only increased very slightly to 5.29. And as you can see here, the amount of light blue seen on the floor plate has been reduced significantly from the previous one. And so that seems a lot better for structural integrity. And so finally, we replace the beginning geometry with the optimized geometries. And so with the geometries we have here, from the beginning, we've replaced them with the optimized geometries, which this model can then be used to be rendered out into using like shading details and accurate lighting. And so finally, from that, we can calculate results. And so the results that could be calculated are the volume and the weight of, I guess, the entire building. And to calculate the volume remaining, we essentially multiply the original volume of a geometry. In this case, I just took the beam as an example. And so with the percentage of the material removed. And in this case, 50% of the material removed. And so it would just be 2 meters cubed remaining. And just to find the weight, it's very simple, just finding the weight value per cubic meter of any material. We could multiply that from the final material remaining to find the weight of, I guess, the beam in this case. And this could be, this process can be repeated for the columns and the floor plate to essentially find the overall weight of each of those components. And then this can then be multiplied by however many columns, beams, or floor plates however many columns, beams, and plates, floor plates are in the building. And so with that material reduced, we can either essentially use that material elsewhere, either to build new buildings or even build taller buildings. As the weight is also reduced, we can essentially build taller on top of an existing building, as the structure was not affected while the weight was, so we can essentially build more. And so to conclude, I have some limitations and, I guess, opportunities of my research. One of the limitations was that Amoeba is run through the cloud, and so with each new iteration you want to run through, you would have to manually, I guess, rerun the optimization, which would have to then be sent to the Amoeba services. This is essentially what cloud computing is. It's just we send information to an external server and they send information back. And so with this, it's really hard to, or I guess, automate this process of design. There would have to be a lot of manual inputs required. But yeah, that's, yeah. And so Amoeba also occasionally does not optimize, I guess, properly. As you saw before with the floor plate, I specified 50% of the material to be removed. And so while it removed 50% of the material, it did not take into account its structural integrity overall, but it just kept removing. So with that, we have to double check all the data and information we gathered to, I guess, with our human intuition, select a design that properly has the right structural integrity while also removing material. Also, a minor thing, the building script I've created only works with 90-degree angles. This could be problematic in cases of doing this for a wide variety of buildings, such as anything that could be round, or a building that could be round or not formed using 90 degrees. And finally, through this research, I guess the implications could be that as cities are already existing, buildings are already in place and were already constructed. And so if we want to build taller, we don't necessarily have to demolish those buildings and rebuild the building taller. We could build on top of the existing building, and with this method, we'll be able to make this more viable, as the structure on top of the building would be lighter through the topological optimization. And so this could be a new way in which we design the future, although there are other limitations such as machining costs and machining times. Right now, topological optimization, the geometry produced from those are quite complex. And so with traditional machining practices, they might not be able to be done, although 3D printing is now a viable process in which we design. So that could be a direction in which we go to for this project. Thank you for listening.
Does Amoeba take material properties?
Yeah. Yeah, it does take material properties. I think for the ones I've done, I used the default material property, which was essentially steel, which is, yeah, it has the material listing, and that was the default one. There was none for wood, but you can actually import a panel into it and just write the material properties inside, or a GeoJSON or JSON file, and import that material property into Amoeba. So yeah, you could use multiple materials.
I think, again, I know these projects quite well. I think you've resolved many of your starting issues, especially the geometry problems that you had at the very start, where there was basically some technical issues with the actual geometry inside Grasshopper.
Yeah.
I think the implementation that you used for the ending analysis of the whole building is quite valid, actually. Because in terms of construction, I think most components these days, you standardize and you mass produce, there will be some sort of cost or carbon reduction instance. Yeah. So I think in terms of the overall project, it's quite interesting to see you know, this kind of optimization process we use. So yeah, well done.
Thanks. Thank you. I didn't do anything. Yeah.
Okay.
12. Okay.
Skip. Okay. Hey, my name's Nimat, and my industry partner is BaitSmart, and my topic for my research project is developing a decision support tool for minimizing embodied carbon in early stage facade material selection. So why do this? Basically, because global warming's bad. The building and construction industry is responsible for about 39% of carbon emissions, which cause global warming, and currently 55% of the global population reside in urban areas, and that's set to grow to 68%, which means more buildings, which means more carbon. So why early stage? Early stage is where the design is most flexible, so that's where you can have the most impact and change without just assessing. You can change the design or the material selection. This is also where 50% of the embodied carbon gets locked away. And only 20 to 25% of the fees are spent. So this makes it the ideal place to make a change. So the question becomes, can we develop a decision support tool for early stage facade material selection to minimize embodied carbon? So the objectives and aims are to create a decision support tool that allows designers to factor in embodied carbon and to create a tool for facades. And so the outcome would be a decision support tool that indicates embodied carbon, and we'll test it at the end to see if it's like accurate and valid. So again, what are we developing? A decision support tool specifically for massing, because that's what's used in early stages. And so hopefully allowing designers to pick materials that hold less embodied carbon when deciding their facade materials. So why do this? Is there nothing available? So with research, what I found was that the tools that are available, they focus on structure, and they're largely predictive because they use machine learning. So they're only as good as their data set. So if you have a dodgy data set, your output's going to be dodgy. Also, they're typologically limited. So like if you have a residential building and then you put in an office building, your output because it's being trained on residential buildings. It's also restrictive in terms of materials and assemblies. Anything new is hard to add to it. And the ones that do all of this and give you something from a live model require a very detailed model, which means it becomes late stage and you can't actually affect any change to the material selection or the design. So how do we do this? We're going to do it using a few programs. Revit mostly was going to hold most of the stuff. Inside Revit, we're going to be using Tally. So Tally is basically a lifecycle assessment tool used by the industry. We're going to have a library of facades inside Revit. The reason for this is you can't apply a single material to a face because a facade contains more than one material. So you have your mullions, which are like aluminium, and then you have your panes, which are glass, and you'll have insulation if you have a shadow box. Inside Revit, we have Rhino inside Revit, and then we'll have Grasshopper inside that. And we use Excel to talk to Tally and Grasshopper. We'll also use Wombat and Human UI, Lunchbox, and Notepad. So the way we're going to do it is that first we have to have So first we have to have an option to clear previous data that might be in there. And then we bring in a mass into Revit. From Revit, we bring the mass into Rhino. Then we cull the top and bottom faces because we're not going to have a facade over there. Then we text tag the remaining faces. This is just to identify what face we're working with. So 1, 2, 3, and 4. And then at the same time over here, we'll be building a library of facade types that we can apply materials to. Once we've applied materials and everything, we export that data out into Excel using Tally. And we bring that Excel into Grasshopper. Then we find the amount of embodied carbon per square meter for each facade type when we select it. So once the facade type is selected and we select our face, we can find the area of the face and the amount of embodied carbon per square meter for the selected facade type. We multiply that by the area of the face that was selected, and we write that into a text file. This is because I couldn't find a program that would append to Excel, so I had to hold the data in a different file. So you hold the data in a text file, and then we repeat these steps for the faces 1, 2, 3, and 4. And then once we're done with that, we can read the text file and export it out as an Excel. So just a quick demo of how it works. Hopefully. Oops, sorry. Okay. So over here we have our facade types and we have our mass. So there's like different facade types, different materials. You have some walls at the back. So just to quickly run through Grasshopper, we bring our mass into Grasshopper into Rhino as a B-rep. We call the top and bottom faces. We text tag the remaining faces, and we find the area of the face to be able to calculate it later. We also read the data from the tally file. We find the facade swatch, and we find out how much embodied carbon per square meter there is per swatch. And we bring that in, we multiply that by the area of the face. And then we save that data into a text file. And once we're happy with everything we've done, run through all the faces, we read that data from the text file and we save it to an Excel file. So the way it would work, the UI looks like this. On that side, we have like most of the information that's coming out, and so you can select your face and your facade type from there. You also have the UI over here, just because I didn't want people to look at Rhino. It just looks nicer like this. And so all your data is there. So before we start, we need to clear everything. And so once it's all cleared, we can select a face. So for example, face 1. And we can select a facade type. Example, facade type 1. And you can see the amount of embodied carbon that's contained. And as we change the facade type and the face, you can tell the amount of embodied carbon down the bottom changes, depending on material and the facade type that you've selected. And so once you're happy with the facade type, you can hit save, and you can do that for the remaining facade types, so faces, of the mass. So you've got face number 2, and say that's like up against another building, so you want that to be like a brick wall. So you got a brick wall, and then you hit save, and then you can see all that data underneath, adds it to a table, and it also adds it to a graph. So then you can run through the other faces, and I just fast. Oh wait, there we go. Okay, so then save, and then once you're happy and ran through all the faces, you can save the Excel. You can save it as an Excel file for an output. Like for example, we'll just name this one test, and it saves. Hit save. It saves your file, and then that's pretty much the output. So it gives you the face, the facade type that you chose, and the amount of embodied carbon that contains. So in terms of testing, to make sure it kind of makes sense and the output is valid, I use the detail model provided by BaitSmart. So we use 25 King Street, and we use face number 4, which is this face, and we ran it through Tally because we had a detailed model. So we could run it through an LCA tool, and it gave us an output of 171,625. And so then we did the same thing by running it through our tool that we developed, and it gave us, so then we picked face 4, and we used the closest facade type that we had. There's a few key differences between this facade type and that facade type. That's the spacing of the bays. 25 King Street was a lot closer, and the floor to floor height is slightly different as well. For this reason, the output was also different. So we got 145,200 embodied carbon in that face. This is a variance about 15%, and that's due to the fact that we're using the square meterage method, and also it's not exactly the same facade. In terms of evaluation, it would be great, I think, to turn this into a 3D thing so you could understand the depth of the facade, like you can understand the depth of the mass over here, and to somehow embed the data that we get from Tally, the embodied carbon material data, into the tool itself. So next steps and future work. So because there's only 10 weeks, if there's a bit more time, it'd be great to be able to test it in a design workflow to see if the designers actually selected a lower embodied carbon material, And again, to remove tally and embed the tool, maybe apply the square meterage and swatch method to other parts such as structure, build up the library and refine the interface. So hopefully these little research things and like little tools like this can help reduce the amount of embodied carbon the AEC industry produces. Thank you.
Did anyone have any questions?
Right, so like I was hoping that like, for example, if you make like a full, if you were making like a facade that was like full, say concrete or something like that, if you could change part of it to maybe be like aluminium or like glass or something, so it reduces the amount of embodied carbon. It's just you can't, all the facade types are different. Like you can't apply one material. So the reason for the facade types was that you could apply the material to the facade type and then bring it, if that makes sense.
It's more like if you just have like a box in
Yeah.
place and you rotate it.
Yeah.
The rotation will be a bigger component.
Oh yeah, because of the sun and everything. Yeah, yeah.
I just wondered if you had kind of, okay, so like 70% of it is orientation and then like we're working with this remaining.
Oh no, I haven't done that yet. No.
I think it's a great project actually. Like embodied carbon is a very a current issue. I think most architecture firms are dealing with. And like at the end of the day, you created a very kind of detailed and it uses quite a few suites of software.
Yeah.
My question is really which process or which part of the process in terms of the software do you think could be a bit optimized or streamlined to help you kind of like, you know, sort all your data out and
Yeah,
help with data as well?
I think it would probably be the tally part. Like I'm not too much of a fan of tally. Yeah. I'd rather like have a database that I could pull from straight to like, rather than run tally on the facade type and then get that data. If I could run a database on that, like as if in a database that was embedded in the tool, rather than have a separate thing, if that makes sense. So that's the thing I think could be optimized, because you're using like a whole other plugin to do a thing and then bring it in. If it was already inside, that'd be nice. Yeah.
Essential for a process.
Yeah. Yeah.
Thanks, Nima.
Thank you.
Yeah, perfect. Yeah, thanks. Good to go. Okay. Hi everyone, I'm Zach and I've been working with BaitSmart. Thanks for coming. Over the course of the past 10 weeks to produce this thesis. So it's called Casing the Joint, predicting embodied carbon in early stage geometry using case-based reasoning. So as designers, we make hundreds or thousands of choices over the course of our projects. Sorry, is that? Okay, cool. Yeah, each and every one of these decisions that we make is important, and it contributes to the design's aesthetics, its performance, its costs, and of course its toll on the environment. So imagine that you could measure the weight of all of your decisions and see which ones made the biggest difference over the course of a project. So we know for a fact that decisions made in the earlier stages of design tend to be more influential and have a higher opportunity to enact change. So why is the analysis of a building's environmental impact, which is a key principle that should inform design decisions right from the start, why is it not done until the very end of a project? So for context, we already know that human activities have seriously impacted the Earth's climate. Each year, building and construction accounts for over a third of the planet's global energy use and a third of our energy-related carbon emissions. This genuinely surprised me during the research, but it makes sense considering the enormous supply chain needed to keep up with increasing population and rapid urban growth, which itself will produce 230 billion square meters of new developments in the next 20 years. That's the equivalent of the city of Paris every week. This research, of course, doesn't aim to tackle climate change head-on, but rather to provide designers with new insights and a new awareness of how their choices impact the environment to help them make sustainable, informed choices in the future. Embodied carbon is a good measure of this impact, and as such, its reduction is an appropriate goal to aim for throughout this research. So embodied carbon is difficult to quantify without detailed design information. This means that only when all the plans have been drawn up and materials finalized can traditional carbon analysis actually begin to take shape. Detailed design information is only available late in the design process, and it's harder and more expensive to change things as the project moves towards completion. If we graph effort against time during a project, you'd find that decisions made earlier tend to cost less, have a bigger impact, whereas decisions made later tend to cost more and change less. This is a fundamental truth of any project, not just architecture, but as computational designers, it's our job to adapt and improvise around these kinds of rules. Whether or not a building has a low environmental impact shouldn't depend on how much money or time a client can or a designer can commit to make that happen. So what is embodied carbon and why is it so important? Embodied carbon is defined as the carbon emitted and expended in a material's production, transportation, construction, and end-of-life phases. So this cycle is referred to as being cradle to grave or cradle to site, depending on the scope of the project. Embodied carbon tends to be a good metric of a building's total environmental impact as it directly relates to its global warming potential, which is another metric I used extensively in this research. Global warming potential is essentially a measure of the atmospheric impact of 1 ton of any material compared to the impact of 1 ton of carbon dioxide on the atmosphere. The higher the ratio it is, the more impactful the material is. Estimating global warming potential is traditionally one of the last things we check off on the list when you're designing a new building. So if this process reveals that important changes need to be made to make it environmentally friendly, it's often too late or too expensive to actually change it. If we were able to accurately predict the global warming potential right from the outset of the project, as designers would be far more informed of the impacts of our choices and have the foresight to make smarter choices earlier. So the process I describe in my thesis would tackle this problem using case-based reasoning, which is a subset of machine learning. Compared to other machine learning methods, CBR has the unique advantage of being most effective with smaller data sets and working well when the target value, in this case embodied carbon, is easily quantifiable, which it is. This method draws from a database of previous examples to find the best fit for a given solution based on a goal that it's been told to look for. So the process follows the 4 R's cycle. First, there's retrieval. A database is searched for a case that is relevant to the target problem. For example, if we want to design an office building with a gross floor area of 1,000 meters squared, for example, out of concrete and steel, the case-based reasoning algorithm will search the database for existing designs similar to that one. And next, reuse, so mapping the chosen case to the target. If the most similar case has a gross floor area of 500 meters squared, but everything else remains the same, it knows that it must double some of the values to match that target. And third, revision. Having mapped the case to the target, we test it iteratively. So we can do this by giving the algorithm a target case for which we already know the embodied carbon value. We just strip the target case of that embodied carbon value before adding it back into the algorithm. And then at the end, we can compare the accuracy of the algorithm to that known value and fine-tune the process until it's as accurate as it can be. And finally, the last step, retaining. This step is outside of the scope of my project, but it could be implemented in a more complete method. So this is where the finished case is actually put back into the dataset. So the goals, what are we actually trying to do? First, we need to generate a dataset I've done this manually for this thesis, but it could be automated using image recognition to gather a firm's existing designs or from Tally, like Nimat said, or it could even be a collaborative interdisciplinary database in the future. Next, we basically do case-based reasoning to it. We create a new target case first and then do the process I just described on the last slide. We retrieve a similar case, adapt it to the target, and then test its accuracy. And then finally, we predict the embodied carbon values. This can be presented in any form, but ideally one that is accessible to designers and stakeholders alike. So that brings us to the question, how can case-based reasoning be used to predict embodied carbon for novel geometry based on data extracted from existing designs? And I guess, is it worth it? Let's find out. So the workflow is done in two main parts. The first half was initially planned to be integrated with Revit and Tally, and it could be in future iterations. But for this preliminary research, a $900 license was kind of out of the scope of the project. Also because removing an expensive software from the workflow means that more designers are able to access it for themselves. The next half is the Grasshopper script, which contains the bulk of the case-based reasoning algorithm, as well as the translation script to be able to format the geometry and dataset for the algorithm to use. So the first thing I did was I imported 15 detailed office floor plans into Rhino. These are all office or commercial floor plans, as this best represents the kind of projects that Batesmart and other firms would apply this tool to. The 15 plans contain a wide variety of geometries and parameters, and with good reason. The 10-week timeframe restricted obviously how large the dataset could be. So in order to better represent the diversity of the floor plans that a future, more expansive iteration would encounter, the wide range of parameters accounts for this, in theory. I then traced these by hand and generated placeholder embodied carbon data for them based on estimated material volume, and used a plugin called Bumblebee to translate the parameters of the geometry into an Excel file. So at this stage, I also created the target geometry, noted its embodied carbon data somewhere outside of the script, and fed it into the geometry without that embodied carbon data back into the script. The algorithm first sorts all the parameters like area and perimeter into a list and shows the breakdown of the area by its spatial type. So this part could potentially be done in the future with an image recognition AI, but for this project, I defined these by hand. They are divided into 3 spatial types, which is circulation, services, and working. So for example, these 3 spatial types were inspired by research done in similar studies, which found a relationship between the amount of embodied carbon in a space and its functional purpose. So for example, services on average have 1.2 times the amount of embodied carbon compared to like a baseline, while circulation areas have 0.8 times. These values would later be used as weighting multipliers in the next stage of the script. So the script then sorts all of these data points and relates them based on a similarity threshold to the target geometry. Like Emily's research before, I used a modified Euclidean distance formula to generate this similarity data, but rather than comparing the distance between 2 pixels, the script maps each parameter with a vector and a location and uses the formula to measure the distance, which is essentially the similarity between the 2 cases. By comparing these distances, the method highlights the most similar case geometry to the target, which the data is then adapted from to form an embodied carbon prediction. So the values from the comparison case that the algorithm chose are then multiplied by the spatial weighting types to find a rough material estimation, and then multiplied again by the difference in areas of the case and the target. So this process basically returns the predicted embodied carbon value, as well as the error percentage for the prediction. And and the actual value that we stripped away from the test geometry before. So does it work? It's not a straightforward answer, but for the purposes of preliminary research, I think the script is pretty viable. An error difference of 21% is certainly not negligible, but for a script that isn't given detailed design information, I was surprised that it wasn't higher. With more time and more iterations and larger data sets, the accuracy and the precision of the script can be defined and the process further refined, eventually enough to possibly integrate it into a real-life workflow. So what are the things that I could have done better? Some of the biggest challenge were learning to write a machine learning script from scratch. So there obviously wasn't an existing script that was similar enough to adapt to this process, apart from a heavily modified Euclidean distance formula. So I had to spend a good chunk of the 10 weeks learning the equations in code to get even a simple comparison algorithm working. Obviously, there's a lot of elements in this process as well that are done manually. The good news is that they are all able to be automated, but given the time constraints, I decided that that was outside of this project scope. What comes next? Like I mentioned before, there are elements that could be automated. In particular, the similarity threshold part of the script has a potential to be linked with either Galapagos or Octopus, which are evolutionary solvers for Grasshopper, in order to find the best find over a series of automatic iterations rather than changing the inputs by hand. I also want to develop a front end for this script so that the results generated are easily readable and accessible, not just by us as computational designers, but by anyone interested in the project. This could be in a format that is able to be integrated into existing workflows, so either a PDF or an Excel table for the raw data, or potentially a browser-based model for the visualization. I just developed a simple mock-up UI for the script to try and showcase the potential for this process to be integrated and used by users who might not be familiar or comfortable with visual scripting. The front end would allow users to directly input geometry and datasets simultaneously, which would be formatted behind the scenes automatically. The UI would show the data related to each geometry and give the user the option to manually change the case and target comparison to see direct comparison between two design options. This UI would run alongside the script and return both the accuracy and the prediction. So, is case-based reasoning a viable method of predicting embodied carbon in early stage geometry? I think the research shows that it is, and that it has the potential to be further explored and refined to make it a fully integrated process in the future. In other words, I think this research has shown that this particular application of case-based reasoning lays some theoretical groundwork for future developments that have the potential to fundamentally reshape the process of sustainable design thinking, especially in these critical early stages of design. Thank you.
Knowing from your machine learning experience, if you kept building up the data, what do you think the results would be?
I think it'd be far more accurate, or at least would be able to measure the accuracy. Like, it's only really once you get 100 iterations that you can find and actually like confidently define an accuracy. So obviously that 21%, that's not accurate. That's just the error difference between the two. So a larger database would definitely give us a bit more confidence in the script, for sure.
I think the time, like 10 weeks, is very short.
Yeah. I mean, no, like I said, like most of the 10 weeks was me just figuring out how to do maths. Yeah.
I think the 15 weeks would have been really interesting to get 15 weeks to see what you got to.
Yeah.
It's very good. It's very good project.
Yeah, I guess admirable project is one of things. Further development, perhaps in a master's. In the mail.
So assuming that your 21% is kind of like ballpark figure of how good you are, that's pretty impressive as a predictive model with such a small number. You have a kind of, I guess one of the ways to describe the structure of this question is, does case-based reasoning work? My guess is the next question, and if you had a question that was automatically generated by Twitter, would be, why did you use linear regression?
Yeah.
If you had to put it in the context of other model methods, what made you pick case-based over linear regression?
That's a good question. I mean, case-based reasoning is pretty similar to linear regression from a mathematical standpoint, but it has the advantage of being able to take in categorical data, not just quantitative data, which I didn't end up actually utilizing to its full extent. There's a process to apply it to case-based reasoning. I think it's called vector mapping, where you assign categorical data vectors that it can describe mathematically, basically. And that was sort of the preliminary goal for this research, was to use that categorical data in the prediction as well. I didn't get around to it like fully, but that was the main goal. I do think case-based reasoning works pretty well with smaller data sets like this, and obviously a good test would be to test it against other machine learning methods in the future. to get like a real measure of accuracy. But yeah. Thanks.
Hey, it's me again, guys. Nayuki, are you there?
Yes.
Oh, perfect. Could you please share your screen so that I'll just turn the mic turn around.
Oh, okay. Here it is. Okay. Can I start?
Yep.
Okay.
Yeah.
Hello everyone, my presentation topic is facade system, sustainable and comfortable architecture by optimizing the facade. As regards to the research background, the optimized facade system will include an analysis of the site's weather and the surrounding environment, identify the user community, improving the architectural material, and the construction performance. In this way, the environment analysis tools could be used in early stages and the test stages. They also influence the performance of designing and the construction, so visualization of facade system also can extend the long life cycle, crucial to sustainable development. Then my research question is, how can environment analysis tools be applied? Which tools could be used in the digital architecture industry? After research, I decided to use Ladybug because import the energy plugs weather files, providing the sun pace radiation maps to visualize the manipulation. The debug also be able to combine with other environmental plugins such as Honeybee to conduct the daylight. The objectives for this project are an automatic facade system including the environment analysis, test temperature, daylight, design aesthetic and logic facade, and the facade connections, test the connectivities and the construction feasibility, construct the traditional architectures with parametric facade architectures, extend the long life cycle of the architecture, achieve the comfortable and the sustainable building. The mentions of this project including 3 steps, the Python and the Grasshopper and the Ladybug and Honeybee. This is the first time diagram, including the analyze, modeled and test, system and output. This slide is the whole workflow for this project, including the environment analysis, test facade design and the retest facade, simulation system and the head preservation system, and output automatic facade system. The features of this project cover the automatic environmental fire extraction, gradient facade design, prefabricated construction of connections, automatic temperature and the daylight test, contrast the comfortable degree between the traditional architectures and the parametric facade architectures, construct the comfortable degree square architecture and the irregular architectures, automatic and visualized facade system. The other shapes in this model, which means surrounding architectures, because in the real life, the surrounding architectures also influence the daylight and the temperature. Here is the Grasshopper script for this project. The first stage is the environment analysis, so combine the Python and the Ladybug to output the initial environmental and the weather analysis. After architects input the place name and the nation name, this system will extract the energy plugs weather files from the internet or user hard drive automatically. Then, the Ladybug will output the sun pace to helping architects find the positive space
for facades because this architecture is located in Sydney. The sun is setting in the north, so the north is the positive side. The architects should adjust the directions of models. For surrounding shapes, these shapes present the surrounding architectures because automatic facade system also associated with the surrounding environment because the situation of the realized the surrounding architectures also influence the daylight and the radiation. By the reason of too many grasshopper scripts for the facade design, so I cannot take screenshots and insert all of them. So I just shows the finished facade design. This facade including a square architecture and an irregular architecture. They both use the gradient facade in the positive sides. I scaled down the pattern and increased the number of patterns from the ground to the roof. This design helped me to observe and test results and construct with traditional and non-gradient facade. This slide is the detail of the facade and the connections design. For the connections of facade, I was considered a sandwich manufacturing process. These connections also take the benefits of prefabricated construction and the maintenance. From the photo, it shows the 4 steps, including the foundation and the connections, and the facade and the connection caps. The features of fabrication are source of a sustainable competitive advantage compared with the traditional technology. Reduce energy consumption to achieve sustainable development. In maintenance, the residents could replace the damaged components of the facade instead of replacing the whole facade. In this way, because of the lower in total construction costs and the maintenance costs, these facade systems also decrease the operating cost of the property developers, contribute to the extended life cycle architecture. Then, for the retest result of square architecture in January, the ladybug tests the comfortable degree of the whole facade, the traditional architecture, which means no gradient facade architecture. The yellow color is the comfortable temperature for the residents. According to data, the percent of time comfortable for the parametric facade architecture is around 76, but the traditional facade architecture is 55. In addition, also could improve the two cold situations. For the test result of the irregular architecture, the comfortable degree of parametric facade architecture is 88%. The traditional architecture is 67%, and they also improve the two cold and the two hot situations. According to this analysis, it is obvious that the parametric facade improved the comfortable degrees. I also calculated the difference of the comfortable degree to hot and to cold situations. For the square architecture, the parametric facade contributed to the percent of time for comfortable and to cool temperatures. However, the percent of time for too hot higher than traditional square architecture. With the help of Honeybee, I detect the parametric facade also enhance the daylight, so I output the difference of daylight. In conclusion, after the initial environmental analysis, the designer should select the building directions manually. The gradient facade could improve the user comfortable degree. The irregular parametric architecture is higher than the square one. The parametric facade have had persuasion effects, reduce the time of two codes. For the square architecture, the parametric facade is ineffective in extremely hot weather. The daylight of the irregular parametric architecture is greater than square one. Improvement of daylight and heat preservation systems of the external wall is benefits of energy reduction. Achieve the sustainable development. The simulation system of facade system helping architects observe and adjust their projects more intuitive. In the future, for the square architecture, improve the facade design to adapt to hot weather. Explore when the data of the comfortable degree changes, what is the relationship between the comfortable degree and the heat preservation degree. Combined with the Python, make this automatic facade system as a grasshopper or Revit plugin. Explore applicable material to extend the duration of the architectures to achieve the sustainable architectures in the future. Yeah, that's all. Thank you for.
Thanks, Naoki. Did anyone have any questions? Comments?
Daniel, do you want to start?
Yeah, I'll start. I think you did well in closing off the project where you found the research objective, I think, where you're comparing the traditional and the your parametric facade. I think you did well also in trying to kind of standardize components that you're analyzing. So well done.
Okay, thank you.
Thank you, Naoki.
Thank you very much.
Stay on the line.
Yes, thanks very much. So next we have Jackie. Jackie, are you there?
Yeah, I'm here.
Wait, let me just Yeah, okay. There we go. Jackie, if you're ready, please share your screen.
Yep. Can you see my screen?
Yeah, all good to
Okay.
go.
Okay, let's go.
Jackie, we can't hear your sound.
Yeah, we can't hear you.
I can't hear?
But your speakers.
Yeah, we can't hear the sound. Did you share your screen with sound? Or
Yeah. Let me try
yeah,
again.
just try it again. Yep.
Maybe I need to this and what about now?
So try and play your video.
It says that because of some mistakes, the voice of the system sharing is stopped. Why? Oh.
Yeah, it's just play it through your speakers. Try and play it through your speakers.
Maybe I need to. What about now?
We can't see your presentation.
Oh.
Yeah, I think you're showing the wrong screen. Yep, we can see your screen. Try and play your.
And the voice?
We can't hear the voice. You got to turn it up.
Also can't.
Yeah, all the way up. No, just turn your sound up.
Yeah, I'm trying. Hi everyone, I'm Joey Huang. My presentation.
Can you make it a little bit louder from your system?
Build material CLP.
Yeah.
Okay. The reason why I chose this
all
topic.
the way up. Okay, perfect. Good.
Yes. the structure of Chinese Asian buildings, which are basically made of wood. All the Asian buildings will be crowded by time, and the Chinese would not exception. Now most of the restoration needs concrete, which can only maintain the appearance, which makes them lose their original meaning. But this new material, CLT, is very suitable for protecting and repairing Chinese Asian buildings, so I chose it. For the current CLT materials, I put forward two research problems. The first is about the structural connection of CLT, which can make them more stable. The second problem is how the hardness of CLT materials is different. In the research, I found that the premise of studying the connection model is to establish a hardness evaluation system of different wood. So my research is more material oriented. I have consulted a lot of literatures. Many of them mention that the strength of CLT board is different because of the wood grow in different areas. Temperature, humidity, climate, and other reasons will affect it. This will lead to the inconsistency of CLT board evaluation system in different regions of the wood, which may also lead to difference between connection methods. Therefore, I think it is necessary to adopt a unified standard to make CLT boards more stable. So my goal is to compare different materials and the different characteristics of wood to determine which factors will affect the stress of wood, such as moisture content and the texture of wood. My ultimate goal is to establish a standard system to evaluate the hardness of CLT board caused by different wood, such as drying some wood with high moisture content to reach the stress standard of CLT plate before manufacturing. To doing this, I contacted a local wood manufacturer and studied 5 different CLT boards. The main materials used were the following 3 kinds of wood. One kind of wood was used as the surface material and the other as the internal material. And through controlling the change of materials to make the 3 tests: shear resistance test, transfer stress test, and pressure resistance test. I selected 2 groups of results. The first group is poplar, outside and inside. And the second group is penis radiata, outside, and poplar, inside. The comparison result shows that the first group have stronger shear resistance, but the pressure resistance is weaker. The second group result is that the shear resistance is weaker and the pressure resistance is stronger. Through the investigation, we found that the only difference between poplar and the penis radiata is moisture content. The moisture content of poplar is lower, so we can roughly judge that if a stronger shear resistance is needed when making skin materials, the wood with lower moisture content is a good choice. The former part is my research on CLT materials. In the later part, my role is to complete the stress analysis of CLT structure in a whole beam workflow. Choosing the optimal CLT size can not only save materials but also reach the stress requirements. and make slicing and typesetting. In this course, I made a hop structure and then used two plugins, Cramba3D and Woodpecker. The role of Cramba3D is to analyze the stress of the overall structure, which can be better optimized by adjusting the size of each part. Woodpecker can import date into cutting date field. This is my workflow. First, I made a whole boundary, changed my model into a half structure, and then used script to make it suitable for various shapes. Analysis and improvements are carried out. After using script to slicing and typesetting of CLT, Woodpecker is used to export a cutting date. At present, I use my own model to test my whole system. First of all, this is my bottom boundary and this is floor, which can be adjusted and applied to my Cramba analysis system. And then I made the conventional floor into a half structure and got control boundary. After that, I use Cramba to analyze the force on it. This part is my whole model, which has three major dimensions: horizontal frame, half structure, and the supporting column. By changing the length and width of each part, the stress of the whole structure can reach the best state. I use a plugin called Genome for autodynamic measurement and gets the specific size data of three main parts. After calculation, I subdivided and sliced the whole structure to facilitate the application of CLT materials. Finally, these plates as cutting materials will be placed on the CLT cutting board for closer layout and use Woodpecker to convert it into cutting date. This is my whole process of my work. As for the time management part, whenever there are some small accents in the process, but I have estimated the time in my workflow part. The whole process is still under control. In the future, maybe I need to improve my calculation process so that the cutting date layout optimization can save most material when cutting. Thank you for watching.
Yeah, this is my opening.
Thanks, Jackie. Do we have any questions? Comments? No? Well done on completing your project. I know it was quite difficult getting your model to work with other people's geometry, but you know, at the end you created your own and you made it work. So congratulations. Moving on. Thank you so much. So next we have Yuki.
Yeah, it's me. Can you hear me?
Yep. So please share your screen, and when you're ready to go.
So, can everyone see my screen?
Yep.
Hi everyone, I'm Wu Yuqi, and now I'm going to introduce my final graduation project. Basically, my topic is about the research of CNC milling machines. So first, I'm going to tell you that why I choose the CNC task. It is about my personal interest, because I am interested in mechanical application like the robots and the cars and so on. So CNC could be the best choice of my research. And then, what is my research question? I have two questions with the task. First is how could multi-axis cutting be realized? Second is what are the main factors that influence the accuracy of the CNC milling? Because for present CNC cutting, it only moves by XYZ axis and it is unwidely and low precision. If it's going to cut the Sophia, the old way is hard to capture the spatial coordinate. But if we change the way of the connection with arm and the file, CNC will be as agile as your hand. Or think that if we could find some alternative method that could combine with CNC milling machines. So for what am I going to achieve is working out an algorithm that could capture the 3D point coordinate and controlling the CNC milling axis through research, and try to figure out the mechanical connecting part of the CNC milling machine, and also a script potentially could control multi-axis CNC milling. The outcome of the research could be a script or kind of method that could control the multi-axis CNC milling. Through the research of the literature, the main limitation of the CNC machine for multi-axis is the algorithm for 3D coordinate capturing and controlling the head, and how the spatial paths could be generated via some programming languages. And Python could be potentially solve the problem. However, Python could be a little bit hard to control for me at this stage. And the machine connecting could be another problem, cause it's pretty hard to combine multi-axis rotating machine with head and ensure the accuracy. In general, my research was mainly on what is the essential logic of spatial movement of these machines. The cutting path was mainly controlled by the coordinate of cutting points. There already are some major logic that transfer the coordinate into cutting language. The main limitation for multi-axis cutting was a mechanical limitation. And KUKA could be an alternative method for the CNC milling machine. And I have tried different cutting objectives and cutting head in Grasshopper. And combining the script and integrate multi-axis cutting could be realized. The different part in Grasshopper means the cutting plan, spatial point, or cutting sequence, and so on. However, KUKA could not replace the CNC machine totally, because there are still some limitations for the KUKA. Cutting machine lack the cutting size, accuracy. So it would be an excellent solution to combine the arm of KUKA with the CNC milling machines in terms of mechanical improvement. After the theoretical researches, I would introduce the practice work in the whole by me work. I was mainly in charge of doing simulation of CNC milling and CLT board manufacturing. And then I'm going to introduce some software I'm using in my Code 3202 project. So first one is the Woodpecker. It is a plugin in Grasshopper that enables users to extend their parametric models seamlessly into fabrication. It offers a number of Grasshopper components that can turn input geometry into fabrication data in BTL format. And the BLT Viva software to open or convert BTL files. And third one is the KUKA. KUKA can enable you to program industrial robot directly out of the parametric modeling environment, including a full kinematic simulation of the robot. The generated file can be executed at KUKA robot without requiring any additional software. And this is the objective diagram that shows what am I going to do. I am going to grab the model and use the bunch of script to outcome the G-code. And this is my workflow diagram that shows my plan to work out this project. First 2 weeks, I'm going to collect model and analyze them. And next 2 weeks, I'm trying to explode the model. And then I put them in a single board and trying to organize them. I also considered about the cost, especially the transportation cost. And then I'm using the script to generate the G-code. Because I can't solve the model that Rob sent to us, so I made a simple one to explain my script. So what can it do? First, I will receive a model from my classmate, but sometimes the model was not perfect, so I developed the first part of my script. And it will analyze the model and give me the conflict point. And then it will optimize the model to make sure there's no conflict anymore. It will cut off the actual part that in each conflict point. After that, I was trying to transfer the whole It will also tell the exact value of different type of cutting pieces and the total consumption of the materials. And this one is the delivery calculation, because I can't connect to the website of the delivery in Australia. So I use the Chinese one. It shows the different type of truck and the cost. The grasshopper will collect the volume of each total price. But it can only consider if I use only one type of trucks. And then it will export the cutting pieces into BTL file. And I can import it into BLT Viewer. This one is the actual work I did. Because CLT board is like a lot of small pieces that combine together, so I made a more complex one. But it is no need, because the board we're using already stick together. So finally, in my project, there are still some technical problems. It is hard to finding the best solution for different CLT size into one single board. And second is the calculation part of the transportation cost. Problems doing research is showing below. So what can I do in the future? I think first is trying to apply the model from the rope to my script, and then is to work out a better algorithm for the transportation cost, because now it can only choose one type of truck. It should be lots of different way of combination. So that is all my presentation. Thanks for listening.
Thanks, Yuki. Does anyone have any comments, questions? Well done on completing your project.
Thanks.
I appreciate that you went a little bit extra at the end of your project to calculate the transportation costs. So well done. I think we're up to our last for this session. Scarlett.
Yes.
Are you ready?
Yes. 1 second.
Oh.
Can I see this?
Yeah, we can see your screen. Oh, we can't see your screen.
Yeah.
Yep.
Hello everyone, the topic of my presentation today is mobilizing 3D printing, exploring a dynamic method to improve the efficiency of 3D clear printing through Grasshopper and a mobile base for 5-axis 3D printing. 3D printing technology is an advanced manufacturing technology which has developed rapidly in the last 30 years. Its advantage lies in the rapid and option manufacturing of 3D shapes, make it widely used in the new product development. 3D printing technology promotes the transformation of the working mode of construction and engineering. It expands the connotation of industrial design. Additionally, it introduces novel and innovative ways to work, design, and produce in developed environments. It shortens the design cycle, saves resources spent on research and development, and reduces enterprise risk. Generally, 3D printing utilizes a range of materials. However, some materials such as metal and clay require additional preparations and post-processing times. These steps can often diminish the viability as construction materials. Consequently, it reduces the efficiency of 3D printing, and his constraint has impeded 3D from being adopted, particularly in industrial production. Based on this research background, I put forward the question how to develop a method that can automatically convert geometry to coding and a script that can stimulate 3D printing so as to explore the method to improve 3D clear printing to make it more viable for application in the architecture, engineering, and construction. This research will focus on the solution to this problem. Before doing my research, I read a number of literature and the literature to strengthen the limitations of the latest 3D clear printing technology. Many exploration study has been carried out in the phase of design and development to find the comparatively optimal system for the follow-up analysis. This offers effective support for the follow-up trials. It offers successful assistance. This research would not be limited to alternate printing conditions for change, such as adding a catalyst to modify the function of printing. It focuses on the conversion of 3D printing system to transform the printing mode by converting the machine to increase the performance of printing. This research proposes a method to explore 3D printing efficiency and quality through a series of iterative experiments. It's useful to explore alternative 3D printing processes, including the study of the printing feasible with non-standard 3D printing material, such as clay and metal, through alternate programming, adopting alternative tools, and alternative printing protocols. In order to achieve this, the present study will develop a script using Grasshopper, Python, and Slice to stimulate 3D clear printing and printing data tooling paths. By converting geometry into code, it is possible to improve the efficiency of 3D printing efficiently without wasting printing material. However, previous research developed new printing methods. In addition to generating more complex geometry shape, now printing methods also reduce material costs and manufacturing time. On the basis, this study will explore additional ways to improve the efficiency of 3D clear printing to enhance future development prospects in architecture and engineering. The new printing method is based on the transformation of the printer. The traditional 3D printer is XYZ 3-axis printing center. This research will design a 5-axis printing center with swing head and rotated table and XYZ 3-axis. Compared with 3-axis processing, 5-axis printing improves the printing mode and improves the printing quality. Multi-axis printing makes use of the change of 2 axes, which can make the position with the max 2 line speed always be used to print the touch object. So it can greatly improve the printing accuracy of the touch object and also greatly improve the printing efficiency. And 5-axis printing can also increase the complexity of printing objects. This research mainly includes 4 brief projects. Slide 3 are GH Python simulation and calculation. Slide 3R is a tool for converting geometry to G-code. Write Python script to extract the data of G-code and convert it into coordinates. Simulation can clearly show the difference between different printing methods. Calculation can directly process the data and analyze the conclusions. This research is mainly divided into 4 parts. Research stimulates 3D printing parts, 3D printing stimulation, and the summary. In the research stage, first such 3D clear printing information is needed to familiarize yourself with relevant knowledge. Secondly, discussions with relevant researchers are required to obtain some and future research. The third step is to establish research objective and finally to develop a general workflow. In the stage of stimulate 3D printing parts, the main step is to find a tool or make a tool to decompose geometries, convert geometries into G-code, and then extract data through GH Python to get 3D printing parts. In the 3D printing stimulation stage, Grasshopper is used to stimulate 2 different printing methods, and the time required for each mode is calculated by mathematical formula. The constructed experiment needs to test different groups of geometries to ensure that there is no contingencies in the experiment. Finally, summarize the data and compare several groups of data to get the conclusion. Because the first stage and the second stage have less tasks, they only need 2 weeks. The third stage has a huge workload compared with other parts, so it takes 4 weeks. Well, the summary only takes 1 week. I read a lot of relevant literature, find the shortcomings of 3D printing, and discuss with a researcher who has a lot of research on it. Finally, confirm the method, improve the printer, add 2 more bearings to the printer which can control the printer base so that it can print more quickly. First, using slide 3R to export the model to G-code, and then write code to extract the coordinates of the print path. However, because the G-code of traditional printing method is different from that of new printing method, the Python code for data processes is also different. The process of making a traditional 3D printing stimulator is divided into 4 parts. First, processing data. The data of geometry are processed separately to make it suitable for 3D printing stimulator, and using Grasshopper to stimulate the nozzle of a 3D printer. The next step is to use Grasshopper to stimulate the printing path of a 3D printer. Finally, turn on the switch and let the 3D printing stimulator start to stimulate printing. The new 3D printing stimulator is a little more complicated than the traditional printing because it has a mobile workbench and it's more troublesome to process data. The process of making a new 3D printing simulator is divided into 5 parts. First, processing data and using Grasshopper to stimulate the nozzle of a 3D printer. Then stimulating the base of a 3D printer with Grasshopper. The next step is to use Grasshopper to stimulate the printing path of a 3D printer. Finally, turn on the switch and let the 3D printing stimulator start to stimulate printing. The length of material needed for printing is measured by Grasshopper, and the printing speed is controlled. The time required for printing is calculated according to the length and speed. I tested several geometries through GH script for the convenience of comparison. I fixed the printing speed at 100 millimeters per second. It took 6,880.397 millimeters clear and 688.8 804 seconds to print the first geometry with traditional printing method, while 2821.502 millimeter clear and 282.115 seconds were required to print with the new printing method. After testing the same geometry in 2 ways many times and compare the data, the results are that the new printing method takes less time. There's a chart showing the comparison of the 2 ways. Its benefits are that it can model the printing condition before printing, prevent printing defects, waste time, and waste materials. Compared to traditional 3D printing, printing the same image at the same printing speed required a little less time. The different time varied according to the complexity of the model. There is no question that a more effective printing process is of great benefit in the production of AEC. From the structural point of view, the construction measures are very straightforward and the servicing is convenient. If model printing machinery can be manufactured in vast numbers, it would be possible to print more fragile items that could not have been printed before and dramatically minimize the processing time needed for the printing of clear metal and other projects. The downside is that it takes a long time to wait before printing is complete. The time depends on the complexity of the model. Later on, you can change the script to speed up the slicing to suit various projects. Other material can be tested on investigate the practicality of this form of printing. Owing to structural issues, the scale of the printer content is influenced by the work table, making it more suitable for printing small volume pieces. One is the issue of follow-up creations, as this study only used Grasshopper to simulate the new printing, and there is no clear scheme for building a new printer. The second concerns the shortcoming and the limitations of this study. At present, the method used to convert model to G-code are relatively easy and cannot convert more complex models. To progress in the future, it's important to discover a way to create model printers and make the perfect prime a possibility. Develop the configuration of a model printer to transform more complex geometry to G-code, making it commonly available in AEC. The model 3D clear printing process will increase the performance of 3D printing. The hypothesis has been supported by this study. 3D printing technology requires some materials such as metal and clear, which require more planning and post-processing time. As construction material, this move aim to minimize their viability. The performance of 3D printing is thus limited, and this constraint hinders the realistic use of 3D in construction world. To address this problem, this research investigates a new form of printing to reduce the preparation time of 3D metal of clear printing to increase the performance of 3D printing. This research consists of a 5-axis printing core with a swing head and a rotary stand. 5-axis printing improves the printing process and improves printing efficiency. Its two lines will often be used to print the tag object at the top speed location, which significantly increases the printing accuracy and the printing performance of the tag object. This analysis also stimulates two printing processes to test this hypothesis. In total, various 3D printing simulators demonstrated the benefits of the model printing mode to ensure the reliability of the conclusion. In addition to the stimulation of 3D printing, the length of the material and the printing speed needed for printing were determined, and the printing time was estimated using the formula to prevent an accident experiment. The data was compared 3 times. Finally, it was concluded that the model printing process could increase the printing performance of 3D clear.
Thanks, Scarlett. Well, congratulations on finishing. Yeah, I think not sure what happened with the audio at the end there, but it got really fast for us. So right now we're just waiting for the next session, the other session, sorry, to finish. And Hank will join us. Yeah, in about 5 minutes, Hank will join us down, and all the other students as well. And we'll finish off with a closing address. So please stand by. Thank you.
Hi, Daniel.
Okay.
Cool. All right.
Yeah, then take it closer to that.
I don't have a lot to say because it's really freezing in here. Yeah. But this is a bit of a momentous occasion. For many of you, you've just finished, and unless those who are marking your projects are feeling particularly narky, yeah, this is almost the last time you'll be in this space well, certainly the last time you'll be in this space as a student. So you're almost graduates of code, soon to be alum. So I think this is, yeah, pretty special. And I'm not going to cry or anything, but I could. Yeah, first of all, the first thing that we need to do as code is to say thank you. And it's worth remembering, obviously, that this is a design research project, the end of your third year, your graduating year, and it's 2 courses, and it engages with industry. So we're approaching design research through the framework of action research, which, as you know, because I forced you to read several articles about it, is collaborative and participatory, and its core principles involve engaging stakeholders, users, and in many of your case, industry professionals from the AEC industry. And to that end, industry is then fundamental to the success of this particular course. And overall to code, I think we have really great relationships with industry, with the AEC industry here in Sydney, but also now nationally and internationally as well. So the first thank you, I guess I want to give, if anyone's still listening out there, is to our industry collaborators, and they are Batesmart, who came physically today as well as virtually. Thank you very much. BIM Consulting, Cox Architecture in both Sydney and Perth, which is great. First time we've had Perth involved in the research. This year's their first time. Crone Architects, Hassel, and also How To. So what's really impressive about that is we're able to look at problems we can solve in the world beyond the AEC industry, and now engaging, beyond the AEC, engaging with other industries. So that's really exciting. HDR Architects, Pulse Software, and Mott MacDonald. Did I forget anyone? No? So yes, a big thank you to the industry partners. It is a particularly a high pressure time for the industry and for many organisations, and for them to take time to engage with you guys, I think is in 2020 an especially wonderful thing, and also very clever, I would say, thing to do, because as you're all quite aware, organisations and institutions have had to confront digital transformation in an incredibly strange set of circumstances, and very quickly. So they've had to adapt. And while they may have sort of been dancing around the edges of it before, it's really come to the forefront. So even though you guys are not IT professionals per se, your design technology skills are incredibly valuable at this point in time, even more so than they were before. But really the point is that it is great to have industry engaged. So thank you. Now, thank you to you guys. What a tremendous effort. So there's 2 things that I think is pretty special about you guys. In terms of this, you're all very special, but your circumstances particularly. The first thing is that you are a group that has experienced the transition from semesters to trimesters. So yeah, and then your last 2 years of your degree you've done in trimesters. So you've experienced a shit ton of change here at the university, and also this year in the rapid shift to online learning, and you are resilient, and you should know that, and you've participated and you've been happy generally when I've spoken to you, and really friendly, and you know, there's not been a lot of, there's a word I'm looking for and I can't think of it. I know it's shocking because, you know, I'm normally all about the words, but yeah, you've coped with it, at least, you know, in your engagements with me and with Code People really well. And I don't think that can be underestimated, the significance of that shift to online learning, being very isolated, and really having to push through and adapt as we all did to that, to these circumstances, which have been a mix of quite scary and very roller coastery, up and down. We don't quite know where we are, but hopefully there's some, you know, light at the end of the tunnel. Of course, the other people we need to thank are Daniel, who, thank you, Daniel, who is, you know, just everywhere and incredibly efficient and, what's the word I'm looking for? Just great personality, always happy. Like, what is that word? Charismatic? No, that's not it. I don't know. The kind of person that, you know, you just really want on your team. So thank you very much, Daniel. And you've just been so generous with us, with the university and with the students. The director of the degree, Hank Hoiser, thank you very much. And our alum who are giving back all the time back into the university. So thank you very much. And to all of those who joined us online, I can see, and Ben, thank you for always contributing and being enthusiastic and giving great feedback all the time for the students. I think your knowledge and perspective is fantastic for everyone. So yeah, thanks, Ben. Okay, so what have you done? I know.
Thank you to you for all
Oh, okay. Thanks to myself. Thanks. Yay me. All right. Okay, but the last thing I want to say is I'm really proud of you, because yes, you've done a research project. You've done it in an incredibly short time frame of 10 weeks, and you've done it very professionally and diligently. And today, all of the presentations that I saw were incredibly professional and really well structured. You explained yourself, there was clarity in the way you spoke about your projects, and you really took on board the structure of starting with the sort of motivation statement first and really getting to the heart of, why am I doing this project? And I heard a lot of you say that. So why am I doing this? So what's the point of this? And that's really excellent, because this is a great skill to be compelling, you know, in job interviews, when you're writing applications, all of those things. People really respond to that when you're passionate and you believe in what you do. It builds confidence and people feel that confidence. And so I certainly felt today that your presentations were really great, and not just great from a content and a style perspective, but and I mean presentation content, but also from the perspective of the problems, the real and complex problems that you were trying to address. For a lot of you, this is about improving design processes, and it's about improving the knowledge that designers have in the design process and giving them tools to give them a better idea of what the impact of their decisions are going to be ultimately on the environment. And you know, you're all dealing with slightly different topics and different phenomena, whether it was wind or urban greening or, you know, topological optimization. These are all really complex topics, and you've just done a fantastic job, and a lot of them are aligning to sustainable development goals. And I think, to me, you know, that's why I'm proud, because you're not just trying to come up with you know, some fantastically complex looking object. You're actually thinking about the impact that design has on the world, and that we do have a responsibility as designers to do it better and to use these tools to mobilize the industry to do it better, because we need to, because let's face it, you know, the world is, its future is its future is at stake unless we actually really get absolutely serious about engaging with the kinds of data that perhaps people, don't necessarily want to deal with in design. That no, this is got too much carbon in it, and this is going to have a terrible thermal performance, and it's overall, is not going to be good. You deal with that in early stage design, and hopefully, fingers crossed, we're just going to have better design outcomes in the future. And I think that's the future, and I think it should be the future. And that's why I do implore you guys to go out there and make a difference, and to mobilise your tools for good and not evil. And the misuse question is an interesting one, but we won't go there today. But I know you all really want to drink, and we have a tab at the Roundhouse. So I'm going to leave it there, because I think this is possibly the first time in a Nicole's class that we've actually finished on time. So, yeah. Yay. Right, so, yeah, well done. Thanks.